always paranoid about forgetting.
What do we do with the recordings?
They're on YouTube.
We post them on the CC Colloquium website with permission of the speakers.
Excellent.
So some have asked not to have them posted, but most are happy to have them posted.
That's excellent.
It's actually one advantage of this Zoom format is that we end up with pretty decent recordings. When we've tried to do recordings of the in-person ones, they don't come out so well. We don't have quite the right setup, I don't think, yet for that.
Yeah, it has been handy, that's for sure, in all sorts of ways.
All right, so why don't we get started? I think the people signing up have leveled off and it's 3:31. So welcome everyone to CC Colloquium for November 18th. We have a special one today. We're going to be hearing from two of our amazing postdocs here in CC, Melodie and Hannes Bernhardt, and they're going to be introduced by their mentors in just a couple of minutes. Just a quick announcement, there is no colloquium next week because it's the day before Thanksgiving, so we expect that people are not necessarily going to be in a science seminar mood, but there is one more after that on December 2nd, Dr. Owama Shields, so I hope you'll attend that one. It should be a pretty fun talk to close out the semester. And if you have any suggestions for speakers for next semester or the future, please don't hesitate to provide them. I sent around a survey link on behalf of the Colloquium Committee last week, I think it was. I'll put that link again in the chat here for those who are here. If you have a suggestion that you want to make, please do that. We're going to try to pull together next semester's schedule in the next couple of weeks here. And so with that, I gather there are no announcements from CC leadership, although Ramon asked me to remind everybody that we have a CC community conversation tomorrow. So please tune into that at noon tomorrow. And with that, I'm pleased to turn this over to Evgenia Skolnick to introduce our first postdoctoral speaker.
Thanks, Ariel. Hi, everyone. It is my great pleasure to introduce you to Dr. Melodie and introduce her to as our speaker today, or one of our two speakers. For those of you who don't know Melodie, let's see, she got her undergraduate degree in physics from MIT and her PhD in 2017 from Caltech, after which she came to join me and us in CC and my research group, which we call Team Dynamos, part of which you'll understand why when you hear Melodie's talk today. And then very quickly after, just the following year, Melodie won a prestigious Hubble Fellowship and has been able to stay with us for an additional 3 years. So, so we're super stoked that she's here. And let's see, I can also tell you about Melodie's wild astro activities. For those of you who might not know, but CC has been running a wild astronomy outdoors course for undergrads, invented and led by Melodie and fellow postdoc and Team Dynamos member Park Lloyd, which has been a great success now for a couple of years. So you probably aren't going to hear about that today, but needless to say, it's a great part of Melodie's experience and contributions to CC. So anyway, thank you, Melodie. Looking forward to your talk and for sharing all your wisdom on dynamos and radio observations and all that good stuff.
All righty. Thank you, Evgenia, for the awesome introduction. And before I get started, I'd actually like to thank you for being a wonderful mentor over the last several years. I'd also like to thank my close collaborator, Sebastian Pineda, some of whose work I've been doing with him I'll be presenting today. And then also, I'd like to extend a huge thank you to the CZ community for building what I think is one of the most supportive, curiosity-driven, kindest academic communities I've ever had the pleasure to be a part of. So when I do move on eventually, I will very much miss the amazing community that CZ has been. Okay, so since their birth, the planets in our solar system have been interacting with the sun's magnetic activity and solar wind. And in this image of the sun's corona during the 2017—
Sorry, Melodie, I don't think you're sharing your screen.
Oops.
Sorry to interrupt.
Oh, thank you. All right.
I mean, I want to see that solar corona. So
It's beautiful corona. My favorite image to share with people. Okay, is this good? Yes, okay.
Yes.
Okay, so this is the image, that beautiful image of the sun's corona during the 2017 total solar eclipse. And what you can see here is a solar prominence, which is dense plasma flowing along one of the sun's tangled and twisting magnetic field lines. And when that prominence becomes unstable, it can actually violently eject hot ionized gas and magnetic fields that impinge on a planet. And that carries away some of the planet's atmosphere. And so, for instance, during the solar storm, for instance, the flux of oxygen ions escaping from Mars can increase by a factor of nearly 100. So over 4.5 billion years, Mars has lost most of its atmosphere. And we think that its magnetic field may have played a role in the evaporation of its atmosphere. So the engine sustaining Mars's magnetic field shut off early in its lifetime, around 400 million years, leaving only a remnant weak field frozen into its crust and no strong global magnetic field. Now, magnetic fields also influence planetary angular momentum. And so in this really beautiful figure from a paper, believe it or not, we can see that magnetic coupling with circumplanetary disks can actually cause young gas giant planets to quickly lose their angular momentum. And similarly, magnetic torquing can lead to misaligned planetary spin axes. And then finally, since deep interior fluid flows, for instance, from rotation or convection, together with the Lorentz force act as a dynamo mechanism to induce magnetic fields, they also serve as the only direct probes into planetary interior dynamics and properties like, for instance, conductivity, viscosity, density stratification. All of these can influence magnetic field properties like field strengths, topologies, and even time-changing behavior. So for instance, in 2018, a team led by then graduate student, now 51 Peg B fellow Kimberly Moore, mapped Jupiter's magnetic field using Juno magnetometer observations. And they found that while the southern hemisphere is predominantly dipolar, the northern hemisphere is actually strongly non-dipolar. And its lopsided magnetic field suggests that instead of a solid core, Jupiter's rocky and icy core could be partially dissolved into its metallic hydrogen region, leading to a multi-layered stratified dynamo. And then there's Earth. So I always like to come back to Earth because it's where we live, it's our home. And Earth has a strong, large-scale magnetic field with most of its energy in the dipole component, which means, as we like to tell our students in our wild astro class that I teach with Park, Lloyd, and Joe O'Rourke, if you zoom out, it looks like a bar magnet. So Earth is not the only planet in our solar system that has a magnetic field, clearly. And neither can we say that Earth's magnetic field is typical for a planet. And in fact, we don't even really know what typical means yet. And so of the planets in our solar system that do have magnetic fields, their surface average radial fields, magnetic fields, span 3 orders of magnitude. Some planets have topologies that are dominated by dipoles. Some do not, right? And Saturn's dipole moment is nearly aligned with its rotational axis. Earth and Jupiter are tilted by about 10 degrees. Uranus and Neptune are nearly sideways. And you know, if this is the diversity of magnetic fields that occur in just our own solar system, imagine what we can learn from studying the magnetic behaviors of our over 4,000 confirmed exoplanets. So if we want to understand the full range of planetary magnetic fields, we're going to have to look outside of our solar system. And right now there are 4 possible ways of probing exoplanet magnetism. And the first two methods directly measure magnetic field strengths. And in one of them, Antonio Oklopcic is leading the theoretical development of harnessing the magnetic broadening and polarization measurements of the helium-1083 line in hot Jupiter atmospheres. And so we can expect, I think, an uptick in papers in the coming years looking for emission using, for instance, spectropolarimeters like SPIRU. And then we will soon, I think, also see the first detections of pulsing and highly circularly polarized exoplanet aurorae at radio frequencies, like this figure of the first detection of Jupiter's radio aurora by Burke Franklin in 1955. So far we don't actually have any confirmed detections of exoplanet aurorae, but there are many teams, as you can see, working towards this goal. And so in addition to these direct methods, there's also interest in indirectly inferring magnetic fields by measuring, for instance, bow shocks in hot Jupiter atmospheres. And so these bow shocks essentially occur when ionized material from the host star's corona piles up against the planet's magnetosphere. And then finally, we can infer exoplanet magnetic field strengths by measuring the power emitted when a close-in planet's magnetic field interacts with the magnetic field of its host star. And this can manifest as what we see here as periodically varying emission lines that are synchronized with the orbital period of the planet. And this is actually work that Evgenia really pioneered earlier in her career. But instead of studying exoplanets, I actually study planetary magnetism from a different perspective, and that is with brown dwarfs, which are objects that are in between planets and stars. Brown dwarfs, I really think of them as the gateway to exoplanet magnetism. And so, for instance, brown dwarfs and gas giants are expected to share similar convective magnetic dynamos. And because the same physics is relevant for planetary dynamos as in brown dwarfs, we can actually use brown dwarf magnetism as laboratories for studying planetary magnetism. All right, so how do I do this? Well, I study their radio emission. So brown dwarfs actually emit two components of radio emission that we can detect now. And for the rest of my talk today, I'll show you what each component can teach us about their magnetism. So in the first component of brown dwarf radio emission, we look at radio aurorae, which is periodically pulsing and emitted at frequencies that directly map to their magnetic field strengths. And by using aurorae to measure brown dwarf magnetic field strengths, we can then actually test planetary dynamo models. And so here's an example. In this seminal model unifying planetary and stellar dynamos, the thick black line here is a scaling relationship from suites of numerical planetary magnetic field simulations that have been scaled up to stellar parameters, arguing that the thermal energy that's convected in their deep interiors determines the energy of their magnetic fields. And then the black dashed lines are 3 sigma or 99% uncertainties on the model. And last year, a former ASU postdoc who was actually in Team Dynamos before he left, Wilson Cawley, he in collaboration with Evgenia Shkolnik showed that the extra heat deposited by host stars into hot Jupiter interiors, so this planet here, hot Jupiters are very close into their host stars, can account for the surprisingly strong magnetic fields that they inferred from star-planet magnetospheric interaction emission, if we assume that there's an ideal energy conversion efficiency. But the extra heat from the host star is unlikely to be perfectly converted to magnetic energy. And actually, when we look at planetary magnetic field measurements within the context of isolated and cold brown dwarfs, we actually see a really interesting twist, which is that these isolated brown dwarfs, they don't get a boost of extra energy from a host star. And yet, like hot Jupiters from Wilson's study, they also have anomalously strong magnetic fields. And so, this really begs the question, what else, in addition to convected energy flux, contributes to these stronger than predicted fields that we observe in both brown dwarfs and in hot Jupiters? So here, I'm age evolving the previous dynamo scaling relationship for different brown dwarf masses. And the x-axis is age, the y-axis is magnetic energy density, and then the dotted lines all correspond to different masses, which I show you on the right-hand side here. And when we unfold the effects of mass, we can see that mass and convected energy flux together cannot explain the strong fields that we observe in brown dwarfs. So these boxes here are the predicted magnetic field strengths for different brown dwarfs that I measured. And the up arrows here are my recent measurements, which all provide lower bounds of the surface magnetic energy density using aurorae that I detected. So as a rule, we can see that the predictions all underpredict what I'm measuring. And so at this point, radio aurorae of cold brown dwarfs tells us that we need something else in addition to mass and convected energy flux to explain the anomalously strong magnetic fields that we're observing on both cold brown dwarfs and also inferring from hot Jupiters. So around the time when I was wrestling with the data that led to these measurements, Jonathan Gagné discovered that one of my targets is actually quite young and has a mass of only 12.7 plus or minus 1 Jupiter masses. And this is right on the cusp of what we would say is a planetary mass object. And so Evgenia and I, we looked at this really young, very magnetized planetary mass object, and we wondered, does age or characteristics related to age, like excess heat, play any factor in an object's magnetism? And so for one experiment, we obtained 4 to 8 gigahertz very large array observations of the young planetary mass brown dwarf 2-mass 1324. This object is only 150 million years old. It has a mass between 11 to 12 Jupiter masses, and our observation spans 16 straight hours, which is enough for an entire rotation period on this more slowly rotating brown dwarf, which means if it has an aurora, we should see that aurora. And a detection in this frequency range would put it right up here compared to its predicted magnetic field down here. And this is what I saw. Right? Nothing, absolutely nothing. Right? But this is not actually a regular non-detection. This is the deepest radio image of a brown dwarf that's ever been made. And so for those of you who are radio astronomers, the RMS noise in this image is 850 nanojanskis. And in other words, this is 4 times deeper than the observations that led to that first detection of a planetary mass object that I made back in 2018 and 2016 with a radio aurora. And so on the right here, what I'm showing you are the 16 hours broken up into 2-hour integrations. And what I want you to notice is that in addition to the complete lack of detectable non-pulsing emission, there's actually no periodically pulsing aurorae either, right? So, what does the total lack of detectable radio emission from this young planetary mass brown dwarf at such exquisite sensitivities really tell us? Well, by shifting our focus from aurorae to quiescent emission, as I've done during my postdoc at ASU, we can learn something really interesting. So gas giant planets, for which cold isolated brown dwarfs are analogs, they emit 3 sources of radio emission. They have electron cyclotron maser emission from aurorae. Here I'm showing you the UV aurorae for illustrative purposes. They have thermal emission, such as this beautiful image at 8 to 12 gigahertz of Jupiter's clouds. And then they have synchrotron emission from radiation belts. And in brown dwarfs, the thermal emission is too faint to be observable. And so the remaining possible detectable sources of brown dwarf radio emission are not thermal, and they require both magnetic fields and electrons. And so this means that by itself, the lack of radio emission from 2-mass 1324 can't tell us much about its magnetism. Maybe it doesn't have a strong field, maybe it doesn't have an electron source. But together, a population of brown dwarfs might be able to tell us if youth or characteristics of youth play an important role in magnetism. And so I developed a generalized Bayesian framework for calculating the occurrence rate of any steady state source of astrophysical emission or absorption. And I applied this framework to radio emission in brown dwarfs. So you can think of an occurrence rate as how likely an object emits at radio frequencies. If you observed 100 objects and you see that 10 of them are radio emitters, what's the chance that the occurrence rate is 10% or 12% or 9.5%? And the important thing about my framework is that I account for observational effects like each object's distance, the uncertainty on that distance, the sensitivity of its observations, and our best guess for how object's radio emission is distributed. And this is really important to do because maybe an object might have radio emission, but maybe it's too faint to detect because it's very far away. Maybe the observation wasn't sensitive enough to detect it, right? And what I'm showing you here are the results from suites of thousands of simulations that I ran to validate my occurrence rate framework using observation parameters that I've randomly drawn from to reflect the literature. And as you can see, the existing detection rate studies in my field are probably under predicting the true occurrence rate by a factor of 2, right? And the green here shows the simulated emission rates for each trial sample. And the magenta here shows the distribution of detection rates depending on the observational sensitivity. And then the dark blue here are the occurrence rates calculated by my occurrence rate framework. And what I want you to notice is that they trace the actual simulated emission rates really well. And so as a fun exercise, I did this with Teen Dynamos a couple of months ago, and it proved to be really illuminating. So I figured I'd try it with you guys. I'd like people to use the raise the hand function. And who here, raise your hand, thinks that more data, so if I observed 1,000 brown dwarfs as opposed to 100 brown dwarfs, would make detection rates better at recovering the true underlying occurrence rate? So let's see, raise your hand. Awesome, so I'm seeing a whole bunch of hands being raised. Okay, great. So it turns out that more data is not necessarily better, right? You get better precision, but worse accuracy if you don't properly account for systematics. So it's especially important to develop robust occurrence rate frameworks, such as the one that I showed you when we look ahead to, for instance, next generation instruments that will allow us to observe thousands of brown dwarfs at high sensitivities. If we don't do that, then we're going to arrive at the wrong answer, right? And so what I'm showing you here are simulations of how well the credible and confidence intervals for the calculated occurrence rate versus detection rate recover the true occurrence rate from my simulations for observations that have typical next generation instrument sensitivities. And so as we can see that as the data set size increases going down, the detection rate confidence intervals actually do a worse and worse and worse job at capturing the quantity that we're interested in. Okay. So having validated my occurrence rate framework, I then conducted an exhaustive literature search of all radio observations of single brown dwarfs dating back to 1995 roughly, which I fed into my occurrence rate framework. And I ended up with a total sample of about 170 objects. And I found that about 15 to 20% of brown dwarfs have quiescent radio emission, compared to roughly the 5% that Monte Carlo simulations from a different study suggest may have radio aurorae. And so what does this tell us about magnetic fields? Well, aurorae at gigahertz frequencies, they trace kilogauss magnetic fields, roughly 100, 200 times stronger than what Jupiter has. And all brown dwarfs with aurorae also have quiescent emission. And so we know that at least 5% of observed brown dwarfs have very strong magnetic fields. But what about the remaining 10 to 15%? Well, since quiescent emission is emitted via an emission mechanism that manifests at tens to hundreds of harmonics of the electron gyro frequency, they trace magnetic fields that are roughly 10 to 100 times weaker. And so it's possible that what I'm seeing is evidence of a population of weakly magnetized magnetic fields. And pretty excitingly, Harish Vedantham's team recently confirmed my prediction when they announced the first 144 megahertz detection of a very cold brown dwarf, which corresponds to about 25 Gauss fields. All right, so the first thing that we've learned from statistical studies of the quiescent component of brown dwarf magnetospheric emission is that there may be a population of weakly magnetized brown dwarfs. And with this occurrence framework in hand, Evgenia and I could now examine whether or not youth affects magnetism. And so to this end, we observed 19 young brown dwarfs and free-floating planets to search for quiescent radio emission. And the ages of our objects range from 10 to roughly 200 megayears. Masses are between 6 to 73 Jupiter masses. And incidentally, this is actually the original project that brought me to ASU. So on the day of what I later realized was my job interview with her, we ended up conceiving of this very proposal for this project. So a few months passed with no detections. There were some pretty long months, I'll be honest, until finally these two pinpricks of light. So right here, and then this last one right here. So these are the two young brown dwarfs that I detected. They're about 200 megayears, 100 and 200 megayears, about 30, 40 Jupiter masses. And you know, the young age is a reminder of the first detected planetary mass object with radio aurorae, as well as the heightened magnetic activity of young low mass stars, and even Wilson-Colley's inferred hot Jupiter magnetic fields. These all hinted at the possibility that perhaps hotter, younger objects are in general more magnetically active. And yet what we actually observe is very different from what we expected. And so as I show in an upcoming paper, we're finding that youth does not actually enhance the quiescent radio occurrence rate of brown dwarfs. And this tells us something very interesting, which is that in general, both the magnetic fields and the electrons necessary to produce the radio emission seem to stick around for very long time scales. And so, in other words, we learned that youth does not strongly affect magnetism. Okay, so far all of these studies were done with free-floating single brown dwarfs. And so this naturally led to the question, well, what about binarity? Right? Comparing the binary radio, so binaries are when you have basically two objects in the same system. And comparing the binary radio occurrence rate to single objects is tricky, as it turns out, because an unresolved binary will look like it's emitting if one or both of its components are emitting. And so this means that binaries are actually already more likely to be radio bright than single objects. And furthermore, the luminosities of binaries will be different than for single objects. And so in another paper that I just submitted, I worked out all that math. And I also present 3 new observations of binary ultra-cool dwarf systems, including this one on the right-hand side. That's the furthest known binary system at gigahertz frequencies. And then combining my observations with what I found in the literature, I show that even when we account for the effects that I mentioned 2 slides ago, there's actually something about binary systems that enhances the quiescent radio occurrence rate of individual components in binary systems. And so what I'm showing you here in the blue is the radio occurrence rate for binary systems that I have predicted from thousands of randomly drawn single object samples that have a similar effective temperature distribution as the components in my binary sample. And we can see that binaries are much more likely to emit radio emission than what their single object counterparts predict. And so from population statistics of brown dwarf quiescent radio emission, we've learned that there may be a population of weakly magnetized brown dwarfs. And I think that we'll see a number of low frequency brown dwarf detections in the coming years that will really shed more insight into this weakly magnetized population. We've also learned that youth does not strongly affect magnetism, suggesting that the strong magnetic fields that could be present in the gas giant exoplanet population at any age. And then finally, we've learned that something about binarity enhances the quiescent radio occurrence rates. Now, I'm not really ready to say why this is the case, but if you check in with me in a couple of years, I have a few experiments that are in the fire that should give us what I think are going to be some pretty cool insights. And to wrap up before I take questions, I just want to emphasize that this is just the tip of the iceberg. You know, to build on all of the cool results from both my work and others that I mentioned during my talk today, and harness what I think will be the full power of radio, what radio astronomy can really offer the exoplanets community, we really need to be ensuring that next generation radio facilities are supported. And so the next generation very large array and the deep synoptic array, which will be operating at gigahertz frequencies, they're going to be essential for characterizing the magnetospheres of brown dwarfs. Gas giant planets will need the large dipole arrays that operate at tens to hundreds of megahertz, like the Owens Valley Long Wavelength Array, 352 LOFAR 2 SKA low. And then finally, to measure terrestrial magnetic fields, we're actually going to need to go into space, which is pretty cool, above the ionospheric cutoff. And so in that vein, the AeroVista mission is demonstrating vector sensor interferometry technology that will be pretty crucial for space-based dipole arrays. And so with that, I will go back to the conclusion slide, and then I'm happy to take any questions that people might have.
Great. Thank you very much. Virtual applause all around.
Real applause.
As I put in the chat here, please type up any questions you have in the Q&A, or be prepared, or raise your hand and I'll call on you. We have time for a couple of questions. All right, there's an anonymous attendee who asks, how long have we been trying to detect exoplanet magnetic fields?
Oh goodness, like decades. It's been so ever since it was really first detected in 1955, people have speculated that we could use radio aurorae on to find evidence of planets outside of our solar system. So it's been a very long saga, and I think we're very nearly there.
All right, Steve Desch asks, he says, very cool. If binarity is important for radio emission, would you be willing to make a prediction about the radio emission from the brown dwarf J1407, the one with the ring? It orbits a protostar on an apparently eccentric orbit. Should we see strong emission from it?
So I would say that it depends. I think that there is a chance of seeing strong emission from it. I don't know how far it is. If it's something within 40, 50 parsecs, it might be worth checking up on. There's kind of a question as to why binarity enhances the radio occurrence rate. So it could be that the binarity makes it easier for these objects to collect electrons in their magnetospheres to actually emit that radio emission. So for instance, from winds, from a protostar. Or it could be, for instance, that binarity spins up these objects so that they, at really high speeds, that might influence their dynamo mechanisms, or potentially energize the electrons in their magnetospheres enough to be radiating gyrosynchrotron or synchrotron emission. So it sort of depends, but I think at this point, having seen how high of an occurrence rate binaries have, I think that they are 100% a population that people should be going after.
All right, if there aren't any other questions, oh, wait, there is one other one. Is there a correlation between the global magnetic field and habitability of a planet?
That's a very complicated question. So I don't know if any of you were there for Nick Schneider's colloquium talk a couple of weeks ago, but one of the things that he mentions, for instance, is Rory don't really tell you anything about whether or not an object has a global magnetic field or not. And this is kind of in the same vein as we don't really know how, exactly what role magnetic fields play in modulating atmospheric evaporation. And there are simulations that show if you don't have a magnetic field, then you're definitely gonna, the planet's atmosphere is going to take the full onslaught of space weather that's impinging on its atmosphere. But if you have a strong dipole field, then that can sometimes help funnel particles, energetic particles, into the upper atmospheres that can actually energize the upper atmosphere and cause that to evaporate more quickly. And then also the orientation of the magnetic field really matters as well. So if it's sort of oriented a way that's a little bit more shield-like, then that'll provide a little bit more protection than if it's oriented in a way where it's just really easy to funnel those particles into the upper atmosphere. So the short answer is that there are a bunch of really great people, especially on the MAVEN team, who are looking at this with both observations of Mars and also simulations. And then as far as we can do right now is just first we have to collect these magnetic fields and then slowly build up more observations to really be able to say something concrete.
Great, thanks. In the interest of time, I think we need to move on. I see Samantha Briley has her hand up. I'm sorry, Samantha, I think we should move on so that we don't go too far past the half hour. So I'm happy to turn the floor over to Dave Williams to introduce our next speaker.
Hi, everybody. It's my pleasure to introduce Dr. Hannes Bernhardt as our second speaker today. He came to ASU about 2.5 years ago to conduct a postdoctoral project with me involving planetary geologic mapping. He got his BS in geophysics from Ludwig Maximilians Universität in Munich, Germany, followed by a Master of Science and a PhD in Geosciences from the Westfälische Wilhelms Universität in Münster, Germany. And part of his PhD involved making a geological map of the Hellas impact basin floor on planet Mars. So his postdoctoral project was funded by the German DFG, which is their equivalent of the National Science Foundation, and involved geological mapping of the MALEA PLANUM region of Mars. And so I'll turn it over to Hannes. The title of his talk is Geology and History of MALEA PLANUM Region, a New View of Mars' Oldest Volcanic Province. Take it away, Hannes.
Thanks, Dave, for the awesome introduction. I'm gonna go right ahead and share my screen here. All right. So actually, what I'm going to tell you in this talk ties into what we just heard about from Melodie, both in their most recent question that was addressed as well as in her introduction. So this is all about how planetary environments change as a function of their atmosphere. and how the, what are the parameters in that function. What is affecting the climate, what is affecting the atmosphere and its change. So we address that from a geological point of view. So just a short crash course about Mars for those who are not too familiar with the fourth planet from the sun. It is a bit smaller than Earth. The gravity is just 1/3, and the average temperature is significantly lower, as well as the atmospheric pressure, that is the modern atmospheric pressure, of course. However, what makes Mars so interesting and so different from Earth from a geological viewpoint is that the earliest parts of geologic history on Earth, and with the earliest parts, I mean 80% of it are barely accessible. Whereas on Mars, as well as other planetary bodies, but mostly on Mars, we have a lot of surface materials and morphologies that are actually from those earlier periods of planetary evolution, and therefore they can tell us a lot of things that happened on the early planet when the atmosphere was still evolving, or before the atmosphere was stripped away, that is. So with Mars, we face a dilemma that has crystallized over the past 2 to 3 decades. So early on, we observed a lot of features on Mars that pointed to a warm, wet, early surface with a lot of large-scale features that appeared fluvial in nature, transient flooding events, close as well as away from volcanoes, dendritic valley networks, and so forth. Then this was sort of at first confirmed, at least that's what a lot of scientists thought, that with higher resolution data, we discovered more and more of those valley networks, and they seem to be in a very distinct band close to the equator, which would point to a control by the climate, and therefore strengthen the hypothesis of fluvial activity that has formed these features. However, no matter how we model the early atmosphere of Mars, no matter what we put into our recipes for modeling it, in terms of composition, in terms of atmospheric pressure, in terms of solar activity, that is, the early sun was fainter than it is today. But even if we try to nudge that up, we just cannot get to a Earth-like Mars with ambient temperatures that are above freezing and that would allow for those features to be formed as, let's say, rivers as we know them from Earth today. So all the models point to a cold and icy early Mars. So how to reconcile the geologic inventory with the models. So volcanic activity as a climate force and agent has been repeatedly brought forward as one possible way to address this dilemma. Now, my work is about one specific puzzle piece in addressing the question, now what does the geologic inventory say about that? So to go back to this splendid HRSC image showing us the working area here between the South Pole and Hellas Basin, which is where, as Dave already mentioned, I spend most of my master's thesis on, and PhD. So MALEA PLANUM is a very heavily cratered, the most heavily cratered of the large volcanic provinces on Mars. There are many large volcanic provinces on Mars. This appears to be the oldest one. So it is key to understand volcanism and associated resurfacing and so forth. When we talk about the very early periods, that is what we call the Noachian period on Mars. And it also can shed more light on those adjacent areas. Already mentioned the Hellas Basin, the largest topographically well-defined impact basin on Mars. So a enormous depositional sink, as well as, of course, the South Pole, which is right next to it, as we can see clearly in the image, and associated features with the South Pole. So physiographic overview, as you can see, we're not dealing with a well-defined topographic sink or a, we are talking about an area that is physiographically diverse. We are sitting between the South Pole here and the Hellas Basin, which is that huge hole. So those blue colors here indicate low elevations. What immediately strikes the eye are those features here. We have those smaller holes, which are referred to patera. Patera is just a very generic term referring to a deposition or topographic low that doesn't lend itself to an impact crater interpretation. So it is a hole, all right, but we don't think it's formed by meteor strikes, so it's something else. The map that I produced looks like this. So this is what we call a geomorphologic or photogeologic map, one of those terms. This is just for eye candy, so it's a comprehensive map, and there are certain mapping standards established by the USGS and other agencies, which are derived from terrestrial mapping standards. However, very important, of course, on Earth, geologic maps are conducted at least partially based on field work. On Mars, we don't have that yet. So when we talk about planetary maps, they are a Frankenstein monster of a geologic map and a morphologic map. So here you see two versions of the same area in the Arctic, an area I worked on on Svalbard. So they look different. So what we do, we combine morphologic observations with geologic interpretations on those maps. Just for those geologists among you who think like, how can planetary geologists make maps if they don't have field work that can bolster the data up? So that aside, let's go back to the map. So this is the fundament based on which I conducted most of my observations and analyses. So first of all, assessing the geologic inventory of the area. I will focus on two little stories here for the sake of time. And the first story is one that potentially points to a volcanic scenario. So these are all units that I interpret to be of primarily volcanic origin. And I'm going to focus on those aforementioned paterae. So the question is, are they calderas? Because they share a lot of morphologic commonalities with the caldera. Caldera is a volcanic collapse feature like Crater Lake in the United States, and it's one of the most prominent ones. For example, it's a hole created by the collapse of a magma chamber. And those here are really large. So what are the implications, and are they a bit large maybe? So you see the scale bar up here. So we're talking about 200 kilometers in diameter. So are they a tad large? Well, yes, they are, but not in a way that would exclude such an interpretation as a caldera. If you compare them to Yellowstone, or the largest caldera on Earth, Apulaki caldera, which is in the Philippine Sea, the largest of those kind of features on Venus, which is probably also a caldera, or the largest one of that kind, which is almost the same size as what I found in my area, in a different area of Mars called Zetis Major. So they are large, but they're not ridiculously large in a way that would exclude such interpretation as caldera. So this is what one of the calderas, Pitiusa patera, looks up close. You can clearly see that depression and material inside of it. Now, this is a zoom in on one of those materials, which is mapped in red on the map in the background. And this little video shows you the peculiar low-bed lineations that cover those massifs right there. Those are very unique. You don't find them in any other patera on Mars. So we interpret them as the surface material manifestations of folded layers. And so, well, we measure their dip, right? So what any geologist would do in the field too. We can do that via remote sensing. It's been done via remote sensing on Earth as well. All you need is sufficiently resolved topographic data, which fortunately we have here. So this is just an excerpt of the dip angles of the batting attitudes that we derived, 57 of them in total. You can also see fold trains where those dips line up. Those folded layers line up, and there you can derive the strain of the area, which in this case is between 0.2 and 2.2% of shortening. That is a negative strain of 0.2 to 2.2%. So the area was shortened, hence the folding. And how did it get shortened? And why do we find that material only here and not around it, not elsewhere in the entire mapping area? So the material's older than the other materials that forms the planes around it. So there's an abrupt slope break, and there's wrinkle ridges, that is tectonic features in the planes here in purple that are aligned with those massifs here and here, for example. So that points to them being Inselbergs, as in, if we interpret the plains to be volcanic in origin as well, but of later volcanism, they are kipukas, that is stuff that stands out from an embayment of volcanic material. So they're old. They're probably as old as the whole, as the patera, potential caldera, because both the material, the folded material, as well as the caldera itself are older than the surrounding plains, because the surrounding plains infill or embay. So this is our stratigraphic interpretation of the area based on observations on high resolution images, on the topography, as well as the texture analysis, that is, for example, those folds that we see. So this would just be an interpretation of how a caldera looks. Most calderas on Earth look very similar, of course, so that's the fundament of that model. And the younger material partially filling it in. So how do you get that shortening? And this stratigraphic model already hints at that. So if you have a specific type of caldera where a central plug is sagged down as the magma chamber beneath it is evacuated, when the material erupts, suddenly you have an empty magma chamber that collapses. And that collapse, if it's a funnel-shaped caldera, like is illustrated here, we have those on Earth too, then the central plug, as it sags down, will be compressed. It's like squeezing something through a funnel. You compress it. And that compression, how much compression do you have? What is the negative strain that you apply to the area? Now, with a little bit of geometry, you can calculate that, assuming a fault angle here. That fault angle being assumed based on terrestrial analogy and modeling and so forth. And it should be between 50 to 70 degrees. And then we have the entire diameter of the area. And if we do the calculations, we get a negative strain, a shortening of 0.5 to 3.4%, which contains the value that we derived for the folding. So the shortening that we observe based on the folding could be explained by this caldera collapse. So that is a feasibility study that we did pointing to that origin of this large patera. And then if you go further, there are axisymmetric finite element models that also look at where does this shortening end and the extension begin around the shortened plug that sags down into a funnel-shaped caldera. We can measure that here too. The minimum extent of that folded stuff, the red massifs here that we measured, and then the entire diameter of the topographic patera. And that ratio between those two radii hints to the depth of a magma chamber. Again, based on axisymmetric finite element models conducted some time ago, based in a little program called Tecton, which is hopefully going to be revised soon, re-released. So that points to a very deep magma chamber, which is not too surprising based on the size of this thing, a magma chamber around 60 kilometers depth. So the size of the patera would be would not be surprising based on the size of the patera to have a magma chamber that deep. And other examples of magma chambers that are of calderas that are rooted that deeply possible are on Earth would be Madsen Lake in the Cascades, as well as on Venus, Sakaeva patera. How do you get mantle, in this case, mantle-derived magma chamber? How can you get that deep? With the Cascades, it's the extension of the crust that allows it. Here, it might be the circumhellas fault belt. We're sitting right next to the Hellas Basin, remember, and a lot of the thrust faults you see here align well with Pitusa patera. Now, thrust faults are compressional, not extensional, but they're most likely formed as extensional faults that got later reactivated as compressional faults. Because around basins that big, we see that on the moon, we see that on the Mercury, we see that on all kinds of planets, you form those big normal faults, those extensional faults facing towards the basin, and they can later get reactivated as thrust faults, and this is what we see on the surface today. And it lines up very well with Pitusa patera. Now, some mineralogic data to back that up would be really nice. We have none right now, that's a problem. We do have spectral instruments looking at these areas, but they're very dusty. So all we see is dust. But finding mantle-derived, potential mantle-derived materials like high magnesium olivine or something like that, that would be really nice, associated with those folded layers. The dust, however, is giving us a real problem here, but maybe we get lucky in the future and get some less dusty observations. The second story I'm going to tell you is one that is related to flow processes and a possible glacial-fluvial. So these are all the units mapped that are possibly related to erosional as well as flow processes. We're going to zoom into one of those areas here, which is one of the areas with the highest channel density on the entire planet of Mars. This is one, those are two of those other patera, and you can see there's a lot of those channels. Most of them originate close or at the rim of this patera called Amphitrite patera. It's a bit different than the other one we just looked at, and that this is located on a topographic rise. It's not just a hole, it's a hole on a mountain. So it looks a lot like a volcano. So the little flyover this area, you see kind of the channelized flank of this volcano-like, shield volcano-like topographic rise with the actual hole, the patera on top, and all those channels emanating from it. So the channels, they are up to 350 kilometers long, up to 3 kilometers wide, and up to 100 meters deep. So they're quite large. Another part of the story would be that important part to explain here, which doesn't show up in a geologic map, of course, is that according to atmospheric modeling, you would have an accumulation of an ice sheet in this area in the past. So right around where a lot of those channels originate. So I wanted to figure out, so are those channels glacial in origin or volcanic in origin, lava flow channels? Because they all start at this thing that looks a lot like a volcano. So it's one of the densest channel networks on Mars. So is it volcanic or is it fluvial nature? I'm going to spoil you. It might be both. So this is what the area looks like up close, and similar areas on Earth. We have Lascaux volcano in Chile. That is, we have ash flow deposits here that can form a very similar morphology. We have Kamchatka, one of the volcanoes there, where channels are formed by lava and then reused by fluvial as well as glacial processes. You have a glacial tongue within a lava channel, for example, or Teide on Tenerife, where you have an intricate network of lava flow channels. So those were terrestrial analogs I looked at. And the parameters of the channels, axios valles, they are called on Mars, some of them at least, some are unnamed. Those channels in my mapping area on Mars, their parameters in terms of sinuosity, size, anabranching, levees, drainage density, all these parameters that you can analyze, none of them is diagnostic. Those parameters could be, the parameters that I derived, that I measured, could be found in channel networks formed by ash flows, formed by, that is phreatic magmatic, ash flow deposits, volcanic flows, that is lava flows, or fluvial networks, either fed by precipitation or ice. So that didn't get me any further. However, only the length of those channels, 350 kilometers at most, and the very low altitude difference, as the slopes are very gentle, implies a low viscosity liquid. So you have a lot of traverse over very gentle slope. So low viscosity liquids, what could they be? Well, of course, mud or sediment-rich water or cleaner water could solve the problem. However, I want to find out, could it also be lava? Because again, a lot of the channels originate within, close to, or right at the rim of that patera. Here, the rim is breached by one of the larger channels. And this right here is almost 3 kilometers in wide channel with almost 100 meters deep. It's probably deeper than that because it's been filled by a lot of secondary material. So if you apply flow models of lava, how long can lava keep flowing, turbulently flowing, in order to form these channels? So not sheet flow, but turbulent flow. You end up with several months of a 2-dimensional discharge rate of 150 square meters per second, 2-dimensional. Then if you multiply that 2-dimensional flow rate, because you always look at the 1-dimensional model and then derive the 2-dimensional model, you multiply that now with the width of the channel. You get the actual flow volume, the discharge rate, that would be 450,000 cubic meters per second. If you look at this channel, for example, here, that is 3 kilometers wide. That is a lot, but is it too much? No. We have comparable eruptions on Earth. For example, if you look at the flow rates or discharge rates that are associated with the Siberian traps or other formations on Mercury and Moon that imply similar eruption rates. So some other tidbits, there's many other units that I showed you here, not associated with those channels. All in all, there are about 500,000 cubic kilometers of material that should have been removed, because you see erosional remnants, and if you extrapolate that over the entire area of the mapping area, you get volumes on that order. Based on my previous work in the Hellas Basin, I know that about 1 million cubic kilometers of stuff filled that Hellas Basin, and a lot of those channels that I just showed you might have been reused by material from here being transported to up here into the Hellas Basin, where a lot of those channels terminate. So all in all, up to 50% of the material that we now find in the Hellas Basin might have originated here. And it's not just one catastrophic event, but several events. Why do we interpret this to be the case? Several events, not just one catastrophic event, as was suggested previously. We need at least 4 distinct episodes of deposition and erosion over at least hundreds of millions of years, based on our stratigraphic observations combined with the model ages that we derived. So the stratigraphic model I already hinted at, showing you the patera. Those are 2 traverses that I will now illustrate our stratigraphic model on. This is what stratigraphic model looks like, based on looking at each unit contact, which unit overlaps which, is embayed by which other unit, and so forth, as well as some other considerations that inform the depth of units. Tectonic features can do that, how crater look can do that, and so forth, but I will not go into further detail here. This is the area we looked at before, Pityusa, Patera, and then the other parts of the traverse. That's the stratigraphy. Now, we can calibrate the stratigraphy with counting craters. The more craters something has, the longer it's been around, and therefore the older it is. That's a simplistic approach, which I'm not going to dive in more right now. That's enough for right now. So we did a lot of those crater counts, crater size frequency distribution measurements, in short CSFD. Not all units lend themselves to such an approach, but the larger units lend themselves, and then you can calibrate the others. Now, the red bars are the model ages, and now we plot our stratigraphy, our chronostratigraphic model, or the correlation of map units, and you can apply an absolute model age here. Though those are model ages, of course, based on the CSFD measurements. And I will not just, this is sort of a basic summary of the work, as I will now go through the landscape formation model in 3 very quick steps. correlated with other events. Right here, there are other events of the surrounding areas. So if we start off, the emplacement of those purple planes that you see before occurred quite early, but even before that, that patera formed. And according to our observations, it formed as a caldera. So this is the cartoon of that. And the other patera might have looked something like that before they collapsed. Think of, if you've ever been to Crater Lake, you've probably been told a similar story right there. So pre-collapse, those what they may have looked like, and parts of the plains might have originated from those other pateras. As we move on, a lot of those channels are formed and they leave behind material, a lot of which will later be again removed, and probably ice resided on the area as well, because we're close to the South Pole and we have a lot of channels that originate in areas. They have common origins in areas, but there's no other sink there that there might have been a lake and then a lake drain. No, there's just nothing there. So, but a common origin with a lot of channels. So that might imply ice resided there. This is also because of the proximity to the South Pole, of course. There's prone to have been periods of glaciation. And then also the atmospheric modeling that I mentioned before indicates that this area up here, that is where a lot of those channels of that dense network originate. They might have originated with a glacial origin as well, based on atmospheric modeling indicating glacial ice accumulation there. Alternatively, they might have originated just as lava flow channels. And then a combination of both might have possible too, that they started as lava flow channels and were reoccupied by water. As I laid out, both is feasible based on the study that I did. And then other periods of glaciation must have been present because we see overlaps of different units that were eroded, and then another unit came on top of the previously eroded. So there are discontinuities there. So several episodes of deposition and erosion must have occurred over hundreds of millions of years. And probably ash flow deposits, which I did not mention due to the shortness of time, which I saw plenty of too. And then we end up with a current situation. Now, as the last slide to wrap this up, volcanism played a big role, and hundreds of kilometer white calderas imply very large explosive volcanism, most likely, which is bound to have a significant climate effect. And what I didn't mention, the wrinkle-ridge plain, those purple plains, the wrinkle-ridge plains, they probably also incorporate a lot of gases, volcanic gases, and which outgas during their emplacement, and that might have contributed up to 4 millibars of H2 to the atmosphere as well. Short-term climate effects. Material transport, as I mentioned, up to 500,000 of cubic kilometers of material must have been eroded and transported into the Hellas Basin, which you see here as a brighter feature. The dense valley network, the Axios Valles, might have been formed by either low viscosity lavas, komatites, for example, or water, or maybe a combination of both. Started off as one and then reoccupied by the other. And there are also valleys, including mud valleys, which connects the South Pole area, traversing my map area, and end up all the way north in the Hellas Basin. So the area MALEA PLANUM is an important puzzle piece for solving the dilemma of Mars via volcanic activity. Thanks for your attention.
Thank you. More virtual applause and a little bit of real applause here. So in the intro time, I know some people probably need to go, so please, if you need to leave, don't feel bad. We won't hear a stampede going out of the lecture hall as we might in person, but feel free to stay. We can, Hannes, you're willing to answer some questions, I assume.
Be happy to.
So even if it's a little late, so you can lots of praise. Both of you guys are getting lots of praise in the chat here. So thank you, thanks to both of you. So Samantha Briley, you still have your hand up. Is that left over from? I'm going to guess that's left over from the first talk. Oh yeah, you just put it down. Okay. So we'll go over here. The questions are kind of wide ranging. But I'm going to go first. A question by Steve Ruff, which is very on point. So Steve asks, with all of the evidence for explosive volcanism, are you seeing clear evidence for ash deposits?
Yes, I do see compelling evidence for ash deposits, but I was not able to include all these awesome observations in the talk. But yes, the short answer, there are very clear indications for ash deposits. For example, very dark mass wasting of very fine-grained material that is interbedded between coarser material, and similar observations that readily lend themselves to an ash deposit interpretation.
All right, and Paras Andel asks a couple of paired questions. Would the age of the caldera floors be younger than the outer surface? And also, are the ice sheets water or CO2 ice? These are two questions, but.
Okay, the floors of the paterae, so those likely calderas, all but one of them has been completely resurfaced after the collapse formed the caldera. Those plains that I mapped in purple, those wrinkle-rich plains that cover and actually define my mapping area to a certain degree, they now cover and post-date the patera formation. All but one of those paterae, there's one of the youngest of those paterae actually post-dates the plain formation. And but there, and there also I see that the entire central floor sagged down like in a funnel shape and caused the formation of impressive structural features on its floor. But yeah, so they are mostly overprinted by the plains. So the area around the patera is the same surface age as the area within, because they are ubiquitously superposed by the same material. Now the ice so any potential glaciation that I incorporated in my landscape formation model, because I derive glaciofluvial activity from those potential glaciations. The observations of those channels are one of the main points to suggest glaciation in the first place, would therefore point to water ice, of course, because CO2 ice liquefies only under great pressure. So if you have a CO2 ice glacier, like the current polar caps of Mars, at least partially composed of, even if you increase the temperature, you would just sublimate it away. It would not form any associated flow activity. So by that, coming from that, the glaciations would have been water ice.
So Tom Sharp picks up on Steve Ruff's question. He asks, how far afield are the ash deposits?
How far, how extensive are they, and how far away do we find them? That is a very good question, because you find those observations that point to an ash flow deposit interpretation, you can find them very far away from those potential calderas, 2,000 to 3,000 kilometers away. And the question is, are they still related to that, or are they of different source? For example, they are also not within my mapping area, but within material that reaches into my mapping area. There are observations of, I made observations of columnar jointing within very dark material. So they are clearly, those were clearly in place as very hot material, then cooled top down, which we think is columnar jointing forms, and very fine-grained dark material around it. So very clear indications for an emplacement as, and based on the topography, they're probably atmosphere derived. So very clear indications for an ash deposit, not necessarily ash flow, but ash deposit in general. However, are these really related to those very patera? That remains unknown, of course. We cannot determine that from photogeology and geomorphologic observations. But my guess would be yes. I mean, those are big calderas, the biggest on Mars. So they would be the closest and most likely sources for that. So potentially extremely extensive ash deposits.
Okay, and we'll just do one more question if you don't mind. It's sort of a more general one. Is the process of evolution of similar craters in different planets similar with respect to period of evolution, topography, etc.? Taking a little bit away from Mars.
If with craters, the paterae are referred to, those potential calderas, which look a lot like craters, or they sort of are craters. Right. The word crater is very very dubious, right? So not impact crater, but volcanic crater. In this case, right. A caldera is a collapse crater. So we find those kind of features on Earth, on the Moon, and in different versions, varieties, and sizes. On Earth, Earth's moon, Mercury, Venus, Io, and in all cases they share certain key characteristics. They are rimless, sort of round depressions that are usually bound by normal faults, indicating material slumped inwards. And they are sometimes surrounded by associated deposits. Now, and they're usually surrounded by other morphologic features that are indicative of volcanic activity. And we derive most of our knowledge from Earth, of course, where we have in situ as well as geophysical assessments of these features, very important as well. The gravity assessments, the seismic assessments, and all these things, which are lacking on Mars. Unfortunately, still mostly gravity we have, but it's very lowly resolved, not sufficient, probably. And so they all lend themselves to such an interpretation. But there, of course, are alternative interpretations. Here we have a very good case for volcanic activity. But for example, on the moon, there are other features that are other possible explanations, and there are some that are more iffy than others and so forth, but they occur on all terrestrial planets and even on Io as well.
All right. Well, thanks very much. In the interest of time, I think we got to wrap it up. Thanks for going a little long. Thanks to both of you, Melodie and Hannes. It's we don't get to hear from our postdocs enough, so it's really great to be able to have these presentations. So thanks to both of you for taking the time to do this. It was really wonderful, and everybody enjoys it.
Thanks for having us.
From the chat. I'll save and send you the chat so you can see that later. But thanks everybody, and we'll see you. Have a great Thanksgiving, and we'll see you all in a couple of weeks. And don't forget the community conversation tomorrow.
Take care. Bye bye.
Bye bye.
Bye bye.